So welcome to section 5.3. So section 5.3, we're going to take a look at something called a Riemann sum. I know I've used that term a couple times already. And we're going to connect it to the idea of the definite integral. Okay? We just have three objectives here. That is to understand the definition of Riemann sum, use definite integrals, and evaluate definite integrals. Okay. All right, so Riemann sums. The area problems we were working on in section 5.2, the last section, were an example of a Riemann sum. So they were a type of Reimann sum. The major change, the major difference in this section is that when we did those area problems, the area problems, you had to have something to look like this. You had to have a function that on the interval a to b gave us a region above the x-axis. So it had to be something that was bounded above like that. In section 5.3 here, when we take a look at Riemann sums, what's going to change is there is no longer going to be a need for the function to be positive. The function can be above the x-axis or below the x-axis. It can be positive or it can be negative. And as we said earlier, the subintervals that we use don't need to be equal in width. For simplicity, when we work with these things, we almost always make them equal, but there's no requirement. All right, so let's take a look at this definition of a Riemann sum here. So this is our definition for Riemann sum. And it starts out by saying, find a function f, define it on a closed interval ab, and then let delta be a partition of ab given by the following. Given by x sub 0 is going to be equal to a, the left-hand endpoint, right? X sub n, so x sub 0 is the same thing as a, x sub n is the same thing as b, the right-hand endpoint, and then all the other x's in between are just values somewhere on that interval. So let's start drawing this as a picture. So we have a function that is defined on an interval from somewhere to somewhere. Okay? Now there's nothing about the definition that requires that the function be positive. I'm going to draw it positive from my sketch over here just because it's easier than dealing with it crossing. Okay. But it could be below the x-axis too. It could be negative. So there's our function f of x, whatever that function is. Now we are going to partition this interval right here, this interval, up into a bunch of pieces. Okay? So we're going to rename the left-hand endpoint x sub 0. We're going to rename the right-hand endpoint x sub n, and then all of the other x's are just values somewhere in between there. So maybe we'll put x sub 1 right here, and then maybe x sub 2 right there, and then x sub 3, and so on and so forth. Okay? You notice that those intervals are not the same width. Right? All right. So then we're to here in the definition. So we've partitioned the interval out into a bunch of pieces. How many? N of them. Could be 10, could be 20, could be 1,000. Just broke it up into a bunch. Okay? The delta x sub I is going to be the width of the ith interval. So if I zoom in on this, then this piece right here, that's the interval that goes from on the left x sub 0 to on the right x sub 1. So the width of that interval, that's going to be delta x sub 1, and that is going to be the x sub 1 minus x sub 0 to give us our width. It's the first interval, so we call it delta x sub 1. We find its width by doing the right-hand endpoint minus the left-hand endpoint. Okay? This is our second interval, so that would be delta x sub 2, and that would be found by taking x sub 2 minus x sub 1, and then we could find the width of every single interval, and the width of every single interval is always going to be the delta x sub I, whatever interval you're talking about, the ith subinterval. Okay, then, man, this is getting rough. We're going to pick a value c sub I, to be any point somewhere in that interval. So I'm going to zoom back in again. And so then we're going to say right here is c sub 1. And then right there is going to be c sub 2. That's the point C in the second interval. So if C is a point in the interval, then what we can do is we can use that value C to find the height of the function at that point. So right here would be f of C1, and then over here somewhere is f of C2, and so on and so forth. And that we're back to what we were doing last section, where we're just going to say, if we're doing a summation, if the f of C sub I represents the height, and if the delta x sub I represents the width, and then when we multiply height times width, each of these is going to give us area, but I'm going to put it in quotes because something changed here, right? The thing that changed here is we don't have to have the function be above the x-axis. This doesn't have to be positive. So if our function was below the x-axis, if this was some other function g of x, we can still chop it up. We can still find the height, but now that height is going to be a negative number. And when we multiply it by the width, we're going to get essentially, which we could, geometrically it's incorrect to say this, but we're just going to say it to make it simple. Rectangles above the x-axis are going to give us positive area. Rectangles below the x-axis will give us negative area. And then when we add up all that area, we get the value of the Riemann sum. Positives and negatives cancel. So it would be possible to have a function where the area above was exactly the same as the area below, and you ended up with something that added up to a zero, a net zero. Okay, so Riemann sums. Essentially, the mathematics of it is the same as what we did for those area problems in the last section. The difference is, last section required the function to be positive so we could talk about it as true area. This section, we changed the name. We call them Riemann sums now. And Riemann sums do not require a positive function. So the value of a Riemann sum could be positive in the end, negative, or zero. Okay? And so we are going to define something. We're going to give a definition for the definite integral. Now, if f is a function that is defined on a closed interval a, b, and the limit of the Riemann sums as the partitions approach zero. Okay, so I want to just look at this definition right here. Okay? This is the thing that causes people trouble here. They don't like this notation, this absolute value of delta approaching zero. But what is that saying? All this is saying mathematically is since each width for every interval can be different, make the largest interval go to zero. Go to a width of zero. Approach a width of zero. And if the largest width goes to zero, then all the smaller ones have to be there too. So that's all this is saying right here. This is just saying, chop it up into so many pieces that the biggest one approaches zero. Right? And then if that limit exists, then we say that the function f is said to be integrable on the interval, and we have a shorthand notation. And that shorthand notation is called the definite integral. It defines the function. It defines where you start, that left-hand edge. It defines where you stop, the right-hand edge. And then it has the integral symbol that we learned in the indefinite integration section, which should kind of lead you to where this is heading here in a minute. Okay. All right, so what I'm working with here is I'm working with the idea from last section, area under a function. We're making it more powerful by saying the function doesn't have to be just simply positive on an interval. It can be positive or negative. We're still doing the same thing. We're chopping up the x-axis. We're partitioning the x-axis into little subintervals. We're measuring the functional value, the height, the functional value on each of those subintervals. We're taking height times width and adding them all up. We're taking height times width, adding them all up, and coming up with our definition for area. But remember, I've got that in quotes because it's technically incorrect, right? It's not geometry area, it's calculus area, if you could think about it that way. Where if the function is above the x-axis, it represents positive area for that rectangle, and if the function was below the x-axis, it would represent negative area for that rectangle. And then we add them all up. Now remember, if you're adding up a bunch of numbers where some are positive and some are negative, the answer can be 0, the answer could be a positive value, and the answer could be a negative value. It just depends on where there's more of this function. So if you had a function that somehow from an A to a B, well, this piece is going to be negative, this piece is going to be positive, and depending on which piece ends up being bigger, that'll tell you the value of the Riemann sum in the end. Okay? Then if we take that idea of Riemann sums and take the limit as those partitions approach, the width of those partitions approaches 0, it stops being an approximation and starts being the exact value. And we give a name to the exact value. We call that the definite integral. Okay? The only requirement that we need for our functions, for Riemann sums to work, is it must be continuous on the interval that we care about. Your function can be discontinuous many times, but if we're on AB, it better be continuous on the interval AB. All right, so let's look at our first example. Evaluate the definite integral. So I have a definite integral. My integrand is the function 2x. So in terms of the language of integration, my function f of x is 2x. I have a lower limit of integration of -2. So that means that my a is -2. I have an upper limit of integration of 1, which means that my value v, where'd that come from? B is a positive 1. And now what I'm supposed to do to figure this out is I'm supposed to take the limit of the Riemann summations. Right? Now, just thinking mathematically about this, the function y equals 2x looks like this, right? A line with a slope of 2. My a value is -2. My b value is positive 1. So when I think about what's going on here, I'm going to have a chunk that's below and a chunk that's above, and geometrically, it appears that the -1 is going to be larger than the positive 1. So my final answer should be negative, right? But I'm going to do the math to figure this out, right? So I'm going to say that the integral from -2 to positive 1 of 2x dx is going to be the limit. Now I'm going to change something here, and I'm just going to simply say n approaches infinity, because I'm going to go back to something I remember from last section. And I'm going to use those right endpoints in my Riemann summation so that I don't have to worry about figuring out the partitioning. I'm going to force the partitions to be the same width, and because I'm forcing the partitions to be the same width, it'll make the math happen easier. Okay? I need to know this and this. So my C sub I, since I'm using right endpoints, the formula is A plus I times delta x, where delta x is b minus a divided by n, or 1 minus a negative 2 divided by n, which is 3 over n. Okay. So that means that C sub I is going to be negative 2 plus I times 3 over n, okay, or 3i over n minus 2. Just clean this up. Okay. Now what I need to do is I need to take this, put it there, this, put it there, and see what the math gives me. So now I'm to this. The integral from negative 2 to positive 1 of 2x dx is going to be equal to the limit, as n approaches infinity, of the summation, as I equals 1 to n, of 2 times c sub I, which is 3i over n minus 2, times delta x, 3 over n. Okay? This piece right here is f of c sub I. This piece is delta x. Clean this up a little bit. This is the limit, as n approaches infinity, of the summation as I goes from 1 to n, of, let's see, 2 times 3i over n is 6i over n, times another 3 over n is going to give me 18i over n squared. 2 times negative 2 is negative 4. Negative 4 times 3 over n is negative 12 over n. And I'm going to wrap this up in parentheses so that I know that this whole thing is the summation. Okay, next step. I'm going to start applying some summation rules. So I'm going to take the limit as n approaches infinity of, I'm going to rip it apart at the minus sign and turn it into two summations. One summation, 1 to n, of 18i over n squared, minus a second summation, so I goes from 1 to n, of 12 over n. Okay. More cleaning up. I'm going to get the limit as n approaches infinity of 18 over n squared times the summation as I goes from 1 to n of I minus, well, there's no I in there. There's no formula for, there's no variable summation there, so that's just a constant. So that's just going to be minus the constant multiplied by the upper limit of summation. So now I'm going to use the formula for this and clean this up a little bit more. So now I have the limit as n approaches infinity of 18 over n squared times n plus 1 over 2 minus 12. This whole thing's in the limit, right? Okay, a little more cleaning up. I've got the limit as n approaches infinity of 9n times n plus 1 over n squared minus 12. Well, here, this is one of those horizontal asymptote problems. Because if I multiply it out, I'm going to get 9n squared over n squared. So then that limit is going to be 9. And the limit of 12 as n approaches infinity. Well, there's no n there. So that's just going to be 12. So 9 minus 12, which should give me a negative 3. Now I'm going to check this. I'm going to cheat a little bit. I'm going to go back to my original problem and think of this in terms of geometry. Okay? This point right here is going to have a y value of negative 4. So this negative area here has a base length of 2 and a height of negative 4, so that's going to be a negative 8. The other triangle on the right has a base of 1 and a height of 2. Wait a second. So that has an area of 2. I'm sorry, this one has an area of negative 4. Area of a triangle divided by 2. This one has an area of 1. Negative 4 plus 1. Negative 3 total area. Whew, man, my brain stopped there for a second. Which is the same answer I got down here using this. Now you might be asking yourself, well, why don't you just do that every single time then? Well, I can't, because every single time I do this, I don't get nice geometry figures. I can only do it when I do have geometry figures. All right. So, what does this mean that I got a value of negative 3? It just means there's more below than there is above that x-axis. Okay? So, the definite integral is area, but we only use the word area in a correct mathematical sense if the function is completely bounded and above the x-axis. So only if it's this way can we say this. Okay? If the function ever goes negative on the interval that we care about, because look over here, this function goes negative there, but I don't care. And the reason I don't care is what's my interval of caring? Well, I only care about the interval from a to b. And from a to b, it's positive. So then the value of the definite integral is the area bounded. Okay? All right, so here's a couple examples where they want us to find the area using formulas. So let's look. Okay? What's happening here? What is this notation asking me to do? Well, it's telling me that my function f of x is the horizontal line y equals 5. It's telling me that my lower limit a is 1. It's telling me that my upper limit b is 3. And so if I were to make a quick sketch of this, definitely not to scale. That's the piece I'm looking for. What's the area of that? Well, that is a rectangle. The area of a rectangle, base times height. I have a base length of 2. I have a height of 5. So the value of that definite interval is 2 times 5, or the integral from 1 to 3 of 5 dx is 10. All right, we're at 25 minutes. I would love to keep going, and I will keep going, but I'm going to keep going in the second video.